Welcome to the 16th Flow Seminar. My name is Samuel Horvath, and together with Peter Richtarik, Virginia Smith, Aurélien Bellat, and Dan Alistar, we are co-organizing this seminar. For those of you who are attending for the first time, so Flow Seminar stands for Federated Learning One-Word Seminar, and it was created as a global online forum for the dissemination of latest scientific research in all aspects of federated learning. This includes both theory and application, and areas such as distributed optimization, learning algorithms, privacy, cryptography, personalization systems, and hardware. Yeah, for today's talk, it's my great pleasure to introduce you our speaker, Misha Khodak. So Misha is a PhD student in Carnegie Mellon University's Computer Science Department, advised by Nina Balkan and Amit Tavalkar. His research focuses on foundations and applications of machine learning, most recently meta-learning, unsupervised representation learning, and natural language processing. And before that, he received an AB in mathematics and an MSc in computer science from Princeton University. Today, he's going to tell us about his work on meta-learning in context of federated learning. So Misha, please go ahead, stage is yours.
Great. Yeah, thank you everyone for coming. So today I'll be talking about our recent work in a series of papers that are based on joint work with Nina Balkan and Amit Talwalkar, as well as with Jeff Lee and Sebastian Caldas. And this work will be talking about our work on provable methods for meta-learning and some connections to federated learning and privacy. So since this is a federated learning seminar, in federated learning, a lot of what we want is we want to demand more from our machine learning pipelines than just plain old training of supervised machine learning models. So for example, we want to learn deep learning models that have limited data for each user, but we have a lot of users, so we want to learn one model for many of them or a personalized model. We want to be able, for our models to be able to keep doing well even when the environment changes. So for example, if in standard practices, the time is always changing, and so we want our models to perform well even when according to temporal shifts. We want to be able to, for our models to adapt quickly to new user distributions, new domains, and so on. And we want to be able to do distributed training and inference. All these goals are important aspects of federated learning. And my goal in this talk is to show how these demands can be viewed through the lens of meta-learning, and how we can use this to reason about the statistical aspects of different federated settings. And of course, some demands I haven't mentioned here that we might ask from our machine learning pipelines include privacy and interpretability, and I'll talk about privacy in this talk, but these aren't inherent necessarily to meta-learning, although we can connect them. So to summarize, what I'm going to be talking about is our multitask formulation of objectives in machine learning called meta-learning, which can improve machine learning by learning to learn across tasks. And so this is a very hot field right now. It's quickly evolving, but the methodology is poorly understood. And so what we'll be discussing is meta-learning algorithms with provable guarantees and connecting these meta-learning algorithms to federated learning, specifically personalization and privacy. Great, so let's get started. So in standard machine learning, we have a supervised prediction problem. We have some input X. We have a configurable function we want to learn, and we have some output Y. So for example, in text prediction, which is very popular in federated learning, we want to learn a function that will predict interesting when given the input meta-learning is, because say that's a good output for many people's language models. I hope many of you will find meta-learning interesting after this talk. And so what we want is to find some parameterization of this configurable function theta, such that the output Y is returned when we pass in the input X for all X and Y drawn from some distribution D. And the way we're going to accomplish this is to just use training data from this distribution that we get in some manner. And so this works great if we have a lot of data. We love to apply things like stochastic gradient descent. We'll just randomly initialize data. We'll pick some learning rate, eta, which is going to be positive. And for each sample in our data set, or for each round, we'll sample some data from our training data, which can be a large text corpus like Wikipedia or Twitter. And we'll continuously update our parameterizable function until we get something good So from random initialization, it's going to be a bad output, but eventually we'll train long enough so that we'll get something reasonable as our output. And we'll return this parameterizable function. So once we switch to meta learning, things become a bit more interesting and a bit more challenging. So here we're going to have many tasks, and each task is going to have far fewer examples. So for example, my advisor might say something other than interesting when after the 3 words meta learning is. So for example, she'll say great. My other advisor tries to be one of the grad students and will say something like dope, and so on. So many people will say many different things. Maybe they'll be related, but each person will have not that much data, and so it'll be challenging to learn a good model for these people. So one approach that we might try is to use a single global model, which actually is what's done a lot in federated learning. So here we're going to aggregate training data from a bunch of people, and then we're going to run the old process we did before, SGD, on all this training data, and all the time we're going to get just one model, and it's just going to output one thing for everybody. So we're not going to get any personalization, which might not be what we want in a standard federated setting. Something else we might try is just to train one model per person. So just take Nina's data, but there's not going to be a lot of it. So instead of outputting something like great or even interesting, it's going to output something she says a lot, like she'd like to talk about provable guarantees, so it'll output the word guarantees instead. So there's not going to be enough data to learn a good model. It's also personalized to her. And so the idea of gradient-based meta-learning is to learn initialization for stochastic gradient descent. So instead of using a random initialization, we're going to use a learned initialization phi hat, and then run stochastic gradient descent on Nina's individual training data. And then hopefully it will output something reasonable that will also be personalized to her. And the surprising thing is that this works surprisingly well, and also is a major component of many meta-learning algorithms. And the way we usually do this, so the way we train this initialization is we randomly pick a meta initialization in our domain space, pick some meta learning rate, alpha, and then we're going to sample training tasks and their task data. And then within each training task, we're going to run some learning algorithm that will output some parameter output and use that parameter output to update our meta initialization. And so this can be summarized as just run within task SGD and then update your meta initialization using a meta update step. And then you return this meta initialization that you can then use on either your existing tasks or new tasks that come into your system. And so this actually describes many successful gradient-based algorithms. So for example, in few-shot learning, famous reptile algorithm from OpenAI is basically just runs within task SGD and then updates the meta initialization using a linear combination of the previous initialization and the current initialization for SGD. Even more famous MAMA algorithm just replaces this by regular gradient descent of just one step, and then does a second order update to the initialization. And in federated learning, the federated averaging algorithm is actually almost exactly the same as reptile, in the case where reptile uses mini batch of tasks instead of just one task. And when the server learning rate, so this alpha, is set to 1, so that we always switch from our initialization we used on task or on mini batch T to directly move to the second mini batch as the average of the outputs of within task SGDs. So this setup of meta-learning can describe a lot of algorithms we're interested in, both in meta-learning and also in federated learning. And so we can consider how it might be used for personalization in federated learning. And so the advantages of gradient-based meta-learning is that it's very simple and very flexible. So all you need really is your few-shot training task, so task with not many examples. The algorithm is very general, assumes all you need is gradient updates, and the output is an initialization, so something you can use for many tasks in your distribution. And so what's great about this is that you can use any model that you like. So if you're doing image classification, you can do ConvNet. If you're doing language modeling, you can use your favorite transformer or LSTM model. And so this is great. The question becomes, what is it actually doing? Why do gradient-based meta-learning method work, specifically for personalization? And so what can we prove about these algorithms? And can we use our theoretical insights to design new algorithms for new settings of interest in meta-learning? So to answer this question, I'm going to talk about first in our series of works, which can be labeled Aruba, which is our new theoretical framework for meta learning. And this was joint work with my advisors, Nina and Amit. What Aruba does is it gives the first provable guarantees for initialization-based meta learning. And these guarantees are they depend on this natural notion of task similarity, which we'll introduce. And the reason we need this is because you can't actually expect to do well using multiple tasks. So to obtain personalization, unless the tasks are somehow related, it's going to be difficult to do well on an image classification task if all of you have to support it are, say, language modeling tasks. And our framework is general enough that it can adapt to changing task environments, extend to statistical settings, so to obtain good statistical rates, and also to derive new methods for various multitask settings. For example, we'll see how this works when we talk about privacy. So this is an outline for the rest of my talk. I'll be talking about our framework, what we can do when we only have a few samples, and provide an illustrative result for how to learn initialization, how to actually prove results in the setting. And then we'll talk about applications to privacy. So before I go on, I can pause for questions. Okay. So the way we're going to be studying meta learning is through the lens of online learning. And so many of you are probably familiar with it. And our results do cover a statistical setting as well, so where it's not adversarial. So this we'll be looking at just for simplicity. Online learning is a great tool for studying iterative algorithms. So many of you are familiar with online learning, but I'll go over it anyway. And so what we have in online learning is that we have M rounds that are sequential. And at each round, we pick some action. So that can be viewed as picking a parameter in our parameter space. And some adversary is going to throw us a loss L of I, which is going to be a function of the action that we took. And the way we're going to measure performance is via regret. So how well did we do compared to how well we could have done if we had just played one theta star in our domain space big theta at every step I1 through M. Instead of changing our step to, say, adapt to the losses that were thrown at us by our adversary. And so in the ideal case, regret is going to be 0. It can also in principle be negative. In that case, that means we have no regret. That's going to be difficult because we're in an adversarial setting. The adversary can throw any loss at us. And this all extends to statistical setting through online to batch conversion. And the reason we might care about online learning beyond its elegance is that you can also use it to consider non-IID data and tasks, which models realistic settings such as reinforcement learning, lifelong learning, mobile device settings, changes in temporal, changes over time, and so on. Yeah, as I said before, you can get statistical results using online to batch conversion, and you can adapt a lot of online learning results to various settings in meta learning. So it's very general. But we'll focus on a simple setting, which is just stochastic gradient descent. So what is single task online learning? So here we have some hypothesis class, which is parameterized by our parameter space data, which we're going to use to take our actions. And the simplest thing we can try is online gradient descent. So just randomly pick an initialization, or even just pick the 0 initialization if our domain space contains it. In theta, pick a learning rate eta greater than 0, and iteratively update our chosen parameter based on the gradient of, or subgradient of, the loss function. And at each step, we're going to suffer the loss L of Li of theta I. When we compare it to the best fixed action in hindsight, we can actually get a pretty good result. So the regret is going to be bounded by d times the square root of m. And what's good about this is that as our number of rounds increases, which you can view analogously to as our sample size increases, on average, the loss we're going to be suffering is going to be d over square root m, which is great. It means as m is increasing, we get a lower loss on average. There's also a matching lower bound for any algorithm, not just gradient descent, for this regret. So we can't actually do any better than d times square root m for the regret. And the goal in online learning is you want to get sublinear regret, so that your regret decreases as you see more and more samples. And so in general, this is a good result because we get decreasing regret as you see more samples. But when m is small, which is the case in many federated learning settings, many users don't have much data. It's also the case in standard settings in meta learning, where it's few shot learning. We only have, say, 20 examples per task. We can't actually hope to do well because on average, we're going to suffer d over square root m, and so the error will still be fairly large even when we use all our samples. And so the key question asked by meta learning is, can we do well using multitask information? So when instead of one theta star to compare to, we have a lot of theta t stars, where t indexes the tasks to compare to. And our goal is going to be to do better on average across tasks. And the way we're going to do this, as we discussed before, is to learn initialization sequentially from the previous t tasks when we initialize a new task. Okay, so now we're going to lift our setting of single task meta learning to or single task online learning to multitask online learning. And so we're going to be considering a setting of average regret. So here we have m times t tasks, or m times t data points, so t tasks, m data points each. And we're going to be considering average regret across tasks, so sum over tasks of the previous regret notion. And as I mentioned before, we can't actually hope to do well without the tasks being somehow similar. And so the way we're going to be measuring task similarity in this talk is via a very simple notion of just Euclidean distance of their optimal task parameters. So recall that we're measuring regret based on how well a single fixed parameter would be doing for each individual task. And so if those parameters are similar, we might hope that the tasks are also therefore similar. So for example, if a language predictor has very similar parameters, optimal language predictor for different people has very similar parameters, then those people likely have very similar language distributions, which is going to be true if, say, they share the same language or come from the same geographical region or age group and so on. And so the way we're going to be measuring task similarity is just the average deviation of these task parameters from some mean. And so we're going to say if this task similarity V is much smaller than the domain of the entire parameter space theta, then we're going to say these tasks are similar. And our results are going to scale with V. So the more similar the tasks, the more close together the optimal task parameters are, the better we're going to do in meta learning. So to review our guarantees, we're going to show that we can actually, by doing meta learning, by learning initialization sequentially across tasks, we can guarantee that the average regret across tasks is going to be V times square root m plus a term that decreases as you see more and more tasks. So let's compare this from before to the single task lower bound, which is D times square root m. And so what we've shown here is that by doing multitask learning, we can improve over single task learning so long as the tasks are similar. So long as the optimal task parameters are closer together in the parameter space compared to the whole size of the space. And so what we have here is, as we see more and more tasks, we kind of trade off this need to search through the entire space and basically drive down to the inherent difficulty of the multitask problem, which is just encoded by how different these task parameters are. And interestingly, you can also show multitask lower bound, so that actually we can't do any better than V times square root m. So asymptotically, as we see more and more tasks, we actually can't do any better than the result we showed here. Okay, so I'll pause again for questions before I go on to discuss the algorithm that obtains this result and simple proof.
I would have one question. So for the previous slide, this M for multitask, is it a number of data points for a single task or overall if we are in multitask scenario?
Right, so here M is the number of data points for a single task. So each task has M data points. So in total, we have M times T data points. But if, say, they're distributions, then they're going to come from, so each M is going to come from different distributions. And T here is the number of is the total number of tasks.
Thank you. So it seems that there are no other questions. Okay, please go ahead.
Okay, great, thanks. So the algorithm that we're going to use to actually achieve the result we just showed is actually going to be this reptile algorithm, which I mentioned before. And so what you can get is, what it does is you iterate through your tasks. At each task, you sample distribution or just your task DT if it's in an adversarial setting. And you run within task SGD or online gradient descent on your task. and to output a parameter, and then you update your meta initialization using the output of your within task SGD algorithm. So yeah, to convert standard reptile, you really just have to replace SGD by online gradient descent, which is largely the same thing, just not stochastic. And for simplicity, we're going to consider using, instead of the last iterator, we're going to be using the optimum in hindsight. And since we're in the convex setting throughout this talk, we can actually compute this optimum in hindsight easily by just solving a convex program after seeing all the tasks. And we can also relax this assumption to actually use the last iterate if you assume sort of non-degeneracy of the optimum, so say unique global minimum. And remember that our goal here is to set the initialization at each step to be to achieve low average regret across tasks. And so the key idea of Aruba is to be able to bound this average regret across tasks by this regret upper bound, which is so by optimizing this sum over the regret upper bounds of the guarantees for this algorithm depending on the initialization. And the key reason we can do this is that existing regret guarantees for online learning algorithms are often nice and data-dependent functions of the algorithm parameters. So for example, for online gradient descent, we saw before that the regret was bounded by d times square root m. But if you actually expand this, what it actually depends on is the optimum parameter in hindsight, which is theta t star for task t, minus the initialization used, which is phi. And then so the Euclidean norm squared of that divided by the learning rate, and plus the learning rate times m, where m is the number of samples. And then if you set the learning rate appropriately, so eta is d over square root m, then you'll get d times square root m regret, because the bound on theta t star minus phi is going to be d squared, because that's the domain, the size of the domain space. And so what we can observe here is that this function is actually really nice, right? We have, as a function of phi, this regret upper bound is strongly convex, and it's data dependent. So it depends directly on how close the phi was to the actual optimum in hindsight. And so the key way we're going to do the way we're going to do our analysis is just by studying how to optimize a function of these regret upper bounds. So just minimizing these very nice, often convex or just distance functions of the initialization or anything else we want to tune. And so what our approach Aruba does is just reduces the analysis of these meta learning algorithms to studying upper bounds of within task learning algorithms. And while we're studying regret upper bounds in this talk, because we're studying online learning, in general, you can also extend this to other measures such as, say, risk or empirical risk that we might care about in within task setting. Okay, so how are we going to update this initialization using online learning, and how can we derive this from studying a regret upper bound? So remember that in Reptile, and this also extends to federated averaging, at each step we're going to run within task online gradient descent. And this within task online gradient descent in an online learning setting is going to get this regret of regret upper bound of ut of phi t, where phi t is the initialization we used at task t. So we applied online gradient descent, and then what we can do is also apply online gradient descent on top of these functions ut. So the way we're going to update our initialization using our optimum in hindsight is just by constructing this function ut, and then just applying online gradient descent. So taking the gradient with respect to ut of phi t, and using some learning rate alpha greater than 0. And so taking derivatives here, what we obtain is just phi t minus alpha phi t minus theta t star. And so theta t star is the optimum in hindsight. And so rearranging terms, we effectively get the reptile update, which is we take a convex combination of the initialization we used and the optimum in hindsight. So if we replace this optimum in hindsight by, say, the last iterate, then we'll get exactly reptile. And if you replace alpha by alpha equal to 1, then you'll get exactly federated averaging in the case where you're actually computing these theta t stars from a batch of tasks instead of a single task. And the regret guarantee that we're going to be able to get is also helped by the fact that these UTs are strongly convex. And so the actual regret on just running OGD on these UTs is just log T over eta. So it's logarithmic regret, which is great. As we see more and more tasks, on average, our regret is going to be log T over T, so it's going to go down with an increasing number of tasks. And so this is the way we're going to run our analysis. All we have to do is to control within task performance using our average regret upper bound. So we pick the algorithm we're going to use within task, which in our case is going to be online gradient descent. And we're going to apply, we're going to control it using an upper bound. In this case, it's going to be this nice function UT. And then we're going to separate terms. So we're going to add and subtract. We add the minimum, so the optimum basically in hindsight of these UTs. So the optimum initialization in hindsight basically for these regret upper bounds. We're going to subtract it out and add it on the other side. And so we'll separate the terms to analyze them separately. And so substituting a cross-task online gradient descent and the nice form of this UT function, which is strongly convex, we get this log T over eta T result, just because these regret upper bounds are strongly convex functions of phi. And so this is great. We've now gotten our first term, and it decreases as we see more and more tasks. And on the other side, we see this impact of how closely related these tasks are. So in this last step, what we're going to do is, again, substitute the actual form of our UTs. And you can see that this is actually closely related to what the task similarity we defined as before, right? So this term is almost exactly a task similarity, just divided by 2 times eta. And so what we can get is, here again, we can substitute our task similarity term v squared over eta plus eta times m. And then by setting, again, our learning rate appropriately, we can obtain our result, which is just that our average regret will be our task similarity times square root m. And then we'll have a decaying term that decays as we see more and more tasks, which is great. It means as we continue meta learning, we'll improve our average performance across tasks to just be the inherent difficulty of the multitask environment, which is v times square root. So to recap, what we've achieved is that we can get this guarantee of v times square root m plus a term that decays as we see more and more tasks for learning initialization using an algorithm very similar to Reptile, very similar to federated averaging. And the key point here is that it improves over single task learning. So as long as the tasks are similar enough that v is much smaller than the diameter or radius of the entire space, then you get better performance on average across tasks, because the best you can do by just doing single task learning is just d times square root m. And also this effectively asymptotically matches the lower bound for this task environment, which is also v times square root m. Okay, and finally, before proceeding to some applications, I also want to put our results in context of various other works in federated learning and meta learning. So there's been a lot of recent work, too much to list, in federated learning and meta learning for studying how to optimize them. And there's also been a lot of work analyzing how to do learning theory, so for federated learning, so and for meta learning, so studying what kind of statistical guarantees we can obtain for these settings. The key area that our work focuses on is actually this interplay of learning and optimization. So it doesn't consider convergence rates like the first set of results, and it doesn't just consider statistical learning, so how we can learn optimally as the second set of results does. What it considers is what happens when we actually apply gradient descent style algorithms to the setting of meta learning. And here, what we have is now this interplay of learning and optimization, where there's also been quite a bit of work in the past 2 years or so. And what distinguishes our work from these also is that they were some of the first transfer guarantees for gradient-based meta learning. So guarantees on how you can do on new tasks once you've learned from a task environment. And also we provide a framework which we'll exemplify with our privacy example next, that can design new meta learning algorithms based on just studying the upper bounds of performance measures, so say regret upper bounds, across several different algorithms. And so what we can also get by applying our framework is adaptivity. So we can learn any base learner parameter from data. So for example, instead of just learning the initialization phi, we can also learn the eta. So before we had to set the eta according to the task environment. so the task similarity V. We can also learn how to set it without knowing this environment by actually learning the task similarity. And it's also very general, so we can adapt, as I said before, to different task environments to get statistical rates using online to batch conversion, and to satisfy specializations like privacy, which we'll talk about. So I can pause for questions before going on to the section and application.
Just to recap, please post your question either to chat or raise your hands. Okay, so it seems there are no questions at the moment.
Okay, great. So now that I've introduced our framework for meta learning, which is Aruba, which studies performance measures and how to optimize them across tasks, we can see what we can get using this framework. So we'll study two settings, which is adaptivity for few-shot learning and also privacy and federated settings. So as I mentioned before, maybe learning initialization might not be good enough for doing well within tasks. So specifically, certain model parameters might not need to be updated on every task. And the way we can learn this, whether this is actually the case, is to learn a per coordinate learning rate that is going to be sort of preconditioned, use it as a preconditioner for our gradient descent algorithm. So many of you are probably familiar with things like Adagrad and Atom that do this. But we're going to consider how we might do this in a multitask setting. So what is the multitask version of, say, Adagrad? So the reason why this might be useful, so in the convex case, as we saw before, if the task similarity is just this isotropic distribution of tasks, then maybe at initialization, which is probably going to be somewhere in the middle of these tasks, we don't actually know beforehand which direction we should move in to get to our optimal task parameter. On the other hand, it's possible that the tasks are distributed non-isotropically. And so if we're using the standard XY axes, we don't want the direction X to have a high learning rate, because we see that across many tasks, very few of the tasks deviate in that direction from the initialization at the center. And instead, we want to move a lot in the Y direction, where a lot more of the deviation lies. And so we can get better guarantees than just this isotropic guarantee by studying an adaptive learning rate. And in the neural network case, we can also see why this might be beneficial. So in many cases, we have a deep net where we're doing feature learning at the beginning, and these feature extractors are often shared across tasks. So many people or many different image tasks will want to extract the same types of features from images. But then when you actually apply classification layers, then these might be adapted to new tasks, because the tasks might shuffle labels. They might have completely different labels. And so you want to adapt these classification weights over the same type of features learned. And so what this means is that you want to adapt the higher layers more and not adapt the lower layers less. And this is found to be useful across a variety of meta learning settings, and can of course be also useful in federated learning. And so so we can modify our algorithm to also learn the learning rate in addition to the initialization. So within task OGD, which we're going to learn across our time steps t equals 1 through t, it's before it was just parameterized as a function of the initialization phi t. We can also parameterize it as a function of the learning rate eta t. And as before, our goal is going to be set average regret to be low across tasks, and a regret upper bound is now a function of these two variables. What's nice again is that, as we saw before, the single task regret guarantees are nice data-dependent functions of the algorithm parameters. So here, as before, it depends on the Euclidean distance between the initialization and the optimal in hindsight. And the dependence on the learning rate is just this Mahalanobis norm term, which is a type of norm that depends on a diagonal matrix in this case, which can be viewed as a summation over coordinates. And so I won't go into the details, but you can derive the optimal learning rate by doing some more analysis by tracking some two quantities, which is sum of squared gradients and sum of distances from initialization. And similar to Adagrad, you have to add smoothing terms to get the best results. And what you can obtain is that you can obtain this also t to the negative 2/5 convergence to learning the optimal per coordinate learning rate, eta. So as long as you have enough tasks, you can learn a good direction ADA to move in. Interestingly enough, it's actually very similar to the undergrad direction. In undergrad, you have some learning rate over the sum of squared gradients. And in our setting, you have also a learning rate over the sum of squared gradients, but you also have a multitask correction term, which is the distance from initialization to the optimal in hindsight in the numerator. So it's very similar to undergrad, but it's a multitask correction term that you can actually use to get better results in meta learning on, say, few-shot image classification. So in this example, we'll study how this performs on the standard mini ImageNet dataset, which is a multitask dataset. So you have a couple classes per task, and you have 5 examples of each class, and then you have to use them to predict. And our goal is to adapt a 4-layer convnet to do well on this task. And we compare several examples. So mammal and meta SGD. So meta SGD is basically a per coordinate version of mammal. And then reptile in general uses this atom per coordinate learning rate. But you can also use Aruba instead to learn multitask per coordinate learning rate. And you can do better in, say, the 1-shot setting compared to the 5-shot setting for reptile using our approach. Basically what our approach gives is this also per coordinate variant of reptile as there was a per coordinate variant of mammal. And if we actually visualize the weights of our neural network, we see what we kind of predicted to see, which is that the upper convolutional layers, which are going to vary a lot more across tasks, so their logarithm of their learning rate is going to be higher than the logarithm of the learning rate of the feature extractor layers, which are the first convolutional layers, second convolutional layers, and so on. Okay, and finally, I'll talk about our, how we can use Aruba to drive new private meta learning algorithms, which is very important in federated learning. So the setting we'll study is this personalized federated learning setting, which, as many of you know, contains a massively distributed data set of small sample size users. And we care a lot about privacy, heterogeneity, but these tasks are similar because, say, they're all text prediction tasks just for different people. And as I mentioned before, federated averaging, which is probably the most popular federated learning algorithm, is very similar to reptile as long as you have a batch averaged meta update. And the difference is it's often run without personalization. So you just use the learned phi, so the initialization, on each task without actually fine tuning. This is often because you actually don't necessarily improve performance using personalization, but this can be addressed. So what we're going to look at is first whether we can apply an adaptive algorithm such as our approach to federated averaging. And as I mentioned before, here you just precondition, learn a good preconditioner, so learn a good per coordinate learning rate using our Aruba approach. And what you can see is that you can actually do better on personalization than both a default federated averaging, which is just use the same learning rate used at throughout training to personalize, and also a tuned learning rate when you tune the learning rate on the personalization task. So by just learning the learning rate throughout tasks, you can actually do better. So this is the rightmost column, which is Aruba full. So if you learn a per coordinate learning rate, you can do better than like a tuned version of federated averaging that's tuned for personalization. And this bold red, as opposed to the light red gap, is the gain you get from actually personalizing on new tasks. So you can use our adaptive approach to improve on personalization. And finally, I'll talk about our application to privacy, which is work led by Jeff Lee and also joint with Sebastian and Amit. And the motivation here is that we want to protect user data not just from external entities, but also from the central server, the meta learner. So say some company or some conglomeration, say of hospitals, wants to do some learning, they're going to, perhaps due to legal or ethical reasons, want to avoid sharing data amongst each other or amongst the learner themselves, not just external entities. And most algorithms that do this require these costly communication protocols or things like noisy local differential privacy. And so what we're going to try to do is to get a better privacy utility trade-off by using a slightly different notion of privacy. Algorithmically, we're still going to run within task OGD, but here, as we see, this update theta hat is not private to the central server. So this is the standard federated averaging update or the standard reptile update. It's not going to be private to the central server because it's just this output of stochastic gradient descent, and we have no guarantees for it. Instead, we can run noisy within task SGD, so apply some differentially private stochastic gradient descent algorithm within task. And you can immediately get record level privacy for any model. So you sacrifice the fact that you'll still know possibly the distributional information about the user. So maybe not good for users that continuously spam their social security numbers to their messaging context, but it might be reasonable for, say, if a user is a hospital, you know the distribution of hospital data, but you don't know the distribution of, say, individual patient records, which is what we really care about. And in the convex case, what are results by, again, just analyzing the upper bounds over the performance measures within task SGD get is that you can get convex case guarantees on the transfer risk that again improve with the same distance-based notion of task similarity. So to summarize what our task global notion of privacy does is that you can sacrifice some privacy, so you'll know, say, the distribution of each user's or each task's data, but you won't know record level information, so individual patient data, for example, which is what hospitals care about. And the reason we might be okay with sacrificing this amount of privacy is because we do get a lot bigger performance. So here we compare on the Shakespeare task using the reptile algorithm with personalization. We compare our performance, so our algorithm, which is in orange, for the 3 different privacy budgets, and it's much better than local differential privacy for the same 3 different privacy budgets, and it's approaching the performance of non-private learning on this task. Right, and so by doing this privacy trade-off, we can get much better performance while still maintaining the privacy that we might need for some settings, depending on the use case. So to conclude, the takeaways from our work is that you can use our theoretical framework to analyze existing meta-learning algorithms and design new ones. So you can get provable improvement over single task learning, which is statistically what we care about in meta-learning. And it also implies new ways of how we can think about designing algorithms for federated learning via this equality between meta-learning and federated learning plus personalization. And so one of the applications that come from this is this novel but practical algorithm for differentially private meta-learning. And so in next steps, what we want to do is also to go beyond convexity and linear representation learning. So for example, in recent work at ICML, we've shown that it actually is necessary to study the non-convex case for meta-learning, even if actually the hypothesis class is a linear hypothesis class. So the success of meta-learning, a lot of it is due to non-convexity, although in some cases, this distance-based notion of similarity that we've shown guarantees for does suffice to show, to kind of explain why meta-learning is working. And the other point is that we want to design better algorithms for personalization, so possibly using this framework. And there's been a lot of recent work on personalization in federated learning that's also considered this connection to meta-learning. So this first work by Zhang et al., for example, and we've also done some work in this direction that appeared at the ICML Federated Learning Workshop most recently. And finally, we also want to consider communication and computation considerations of these algorithms for meta-learning, which for now, we've just assumed that we just use the standard federated averaging approach, but perhaps there can be a smarter way of doing things. So yeah, thank you everyone for coming to my talk. You can see more information at these archive links at my website, and we also have a blog post up about Aruba. So thank you.